Welcome, Amira.
Thank you for having me. I'm very glad to be with you today.
It's a pleasure. So you are a cryptographer and protocol engineer. Please, if you can introduce yourself.
Yes, that's indeed. So I guess, I've been working in the Web3 blockchain ecosystem for the last 5 years. I've worked on different projects. The most important one was Consensus. Consensus is the largest blockchain company working in the ecosystem, mostly working on Ethereum. I've also worked on different projects focusing on privacy on the blockchain, whether on Ethereum, Cardano, or different blockchains. I'm also a guest teacher at INSEC Business School and at Paris Saint-Denis. I also give courses online to teach about cryptography, blockchain, whether on the technical or non-technical side. And I help as a consultant different companies to move from Web 2 to Web 3 and find use cases how to use the blockchain in their specific for their specific use case. So that's me.
Congrats. First off, please could you explain what is cryptography and how it is involved in the blockchain ecosystem?
Sure. So cryptography is basically science of encrypting information. It comes from mathematics. It's something in between mathematics and computer science. So it's basically finding these methods of encrypting information, hiding information, so only the people who are allowed to see that information are able to do that. We are able to use these cryptographic methods by applying some mathematical methods, and then we use them in computer science basically to hide, for example, information and to create secure channels of communication between people, like TLS, SSL, or encrypting, for example, information when someone sends an email to you, so only you can open that email and read what you have received, or basically you send transactions, do electronic signature on the internet. So many different applications of cryptography. And actually one thing, because we're talking about blockchain, why cryptocurrency is called cryptocurrency is because it uses cryptography. So it comes from cryptography. That's why we call it cryptocurrency basically, because it uses cryptographic methods to do so.
Perfect. So let's deep dive into cryptography and talk about hash algorithm. For us who don't know, in a few words, a hash algorithm takes an input an amount of data, and comes out with a hash value, and it enables a blockchain to work. Could you explain more thoroughly how a hash algorithm and how they are used in general within the blockchain?
So yes, exactly as you were saying, it takes an input and outputs an output. The amazing thing about hash functions, and one of the reasons why we use them, is no matter what is the size of the input, it always outputs. The output will always have the same size. It will never change. So if you take the whole page of Wikipedia and then you have the output, it's always going to be, for example, if we take SHA-256, it's always going to be 256 bits long. And if you take only one word from that Wikipedia page and compute its hash, it's also going to be 256 bits results. So it's basically one of the advantages is that we use it to reduce basically for example, the result, to make it smaller, and instead of putting, I don't know, a whole text, a whole book on the blockchain, we only put its hash. So instead of putting, I don't know how many gigabytes, megabytes, or whatever, on the blockchain, which is huge and very costly, we only put 256 its hash basically. So that's what we mean by it. And it takes like hash functions are different. Like I was like talking about SHA-256, but there are like different hash functions that we have and use today.
Yeah, exactly. And SHA-256 is the evolved version of SHA-1, which was broken in 2015, as you explained it to me earlier. SHA-1 was designed by the NSA. It was a 25-year-old encryption method, and it was theoretically broken in 2015 and practically broken in January 2020. It's very recent. It took 2 months of work. I read it on a research paper, and 900 GPUs. That's huge, but it does prove that the encryption that we do have today won't be the one that we will have tomorrow. How do cryptographers tackle vulnerabilities of the blockchain, knowing that it is only temporarily efficient encryption that they are creating?
Cryptography, like I said, it uses like mathematical problems. So the security of every cryptographic method is based on the hardness of solving some sort of mathematical problem, or saying that we can only break this in this 2 to the power, I don't know, like 180, 190, for example. So it's not we're saying it's impossible, we're just saying it's difficult. So whenever we design a cryptographic method, we know it could be broken. We're never saying, hey, this will never be broken, this is secure for life. We know that, we are aware of that. But that's why researchers continue to do research. That's why no matter what method we use, we're always going to continue do research to try to find vulnerabilities in that method to make sure whether it's secure or not. And then we're always going to find some replacement to replace it, for example. So yeah, SHA-256, which also was also designed by the NSA. It's a replacement of SHA-1. So when SHA-1 was broken in 2015, theoretically, researchers decided, and basically people who were using SHA-1 decided to move forward and use SHA-2. So SHA-1 is basically the output has 190 bits, and SHA-2 it's different. It would have 224, I guess, bit, 256, or the 512. So different sizes. But what they found in 2015, they found there was a possibility for a collusion, which is basically one of the properties for hash functions is to be collusion resistant. So they found there was a collusion in the algorithm of that hash, and it was the way to compute and to find that collusion. It took less than what a brute force would take. So they've proven at the time that it could be broken. Theoretically, it was broken. So decided it's safer to move forward and use a different hash function instead of waiting to actually someone break it, which happened basically. So yeah, that's why they decided to move to SHA-256. But it was not broken by any attack, real time attack at the time. It was just a safety choice.
Okay. Do you trust SHA-256 for the Ethereum blockchain?
I do. I definitely believe that SHA-256 will be secure for a while before maybe there would be an attack. But I guess you never know. Research is evolving every single day. You never know. That's why we continue and find different algorithms. There is also SHA-512, but it's not that much used by softwares. Today it's more SHA-256, but there are also different hash functions possibilities, and ones that we try to use and we're already using today, not for security reasons, not because SHA-256 is going to be broken or something, but more for efficiency reasons. There is other replacement the Peterson commitments. There is also MIMC hash function. There is the most recent one, the Poseidon hash function, which is used for zero knowledge proofs, it's better to use it because it takes it's less in complexity of calculation. It's better to use it than to use SHA-256. So yeah, there are other reasons to use other hash functions, for example.
Okay. Could you explain what is a zero knowledge proof?
Sure. I guess as the name sounds, it's zero knowledge. So there is no knowledge, there is exactly zero knowledge. So it's basically you trying to prove something to someone without actually showing what you're proving. So I would give you a very simple example. I would ask you to give me a password, knowing if you know the password to enter from a certain door. Let's say it's Open Sesame, for example. Okay. And so you want to prove to me that you know the password to enter to that door, but you don't really want to give me what the exact password is. So what you do is imagine, it's actually the first example that they give in the Wikipedia when they explain zero knowledge, is they give you this drawing of a door in the middle, and then you have one entrance from one side and then the other entrance from one side. So if you're able to enter from one side and then leave from the other side, you actually proven to me that you know the password, because the door was closed and there is no way you could have got out from the other side unless you opened that door. So basically you know the password. So this is a way of proving some sort of information without actually revealing that information. So this is the basic idea of zero knowledge. And there are so many different examples, like the millionaire problem, basically two millionaires trying to prove who is richer without actually revealing the exact amount of money that each of them have. So basically they use zero knowledge, for example, and they can compare the amount of money without actually revealing that amount of money to them or to a third party. And yeah, we have different use cases for zero knowledge, basically.
So nowadays we have a blockchain led by pseudonymity, not anonymity. Would it be possible for zero knowledge to create a real privacy blockchain, or is it an utopia?
So yeah, what we mean actually by pseudo-anonymity is basically instead of putting your name, your full name, and saying this is my account, this is how many bitcoins I have, you're actually using your address, your public address. People think or thought before that this makes it super private, no one can reach you, but actually it's really it's attached to an IP address and it's trackable, and the FBI and others have proven that it is trackable, and they were able for example to find some people who used cryptocurrency in a criminal way, and they were able to track them and find them. So it's not complete anonymity. Zero knowledge, what it can provide anonymity if it's used for identity, for example. So you're hiding, for example, information we call metadata. So it's data that is related to you, your name, your address, the amount of money you have on the internet, all these information that when collected they could be used to track you or to find information about you. If we use zero knowledge or also other cryptographic techniques, we can hide that information and still prove that you're eligible to use, for example, a certain protocol or to send money or something else. So yeah, it can provide more privacy and brings anonymity to blockchain.
Last but not least, this type of layer 2, so zero knowledge, can be used for scalability. It does mean that we could make more transactions in a less amount of time with zero knowledge. But what we do know is that latency, as in Ethereum, for instance, where it's 12 seconds, is necessary for safety. For instance, if I am a scammer and I take all of your money and the block is validated within, 1 second, you won't have the time to react to that scam. But if there is a latency, you could possibly. So if zero knowledge is really improving the scalability of any blockchain whenever it is a layer 2, won't we lose some kind of safety because we will have less latency?
So yes and no.
Mm-hmm.
I agree with you. Like with more latency, we have more security, like safety. Like Bitcoin, it takes 10 minutes to validate a block. So Bitcoin, we could say that it's better, for example, than Ethereum because it's only 12 seconds. But it's different. Like they have different way of functioning. And if we bring like scalability to Ethereum, it will be even less than 12 seconds. It will be like probably like the same amount of like transactions like Visa would do like in a second, which is huge and makes it like allow us to do like real world applications that are not possible today with blockchain technology. What zero knowledge and basically Starks, like actually we use the Starks for layer 2 solutions, the zero knowledge protocol. We use it like, for example, like with sharding. So sharding is a technique that is used in Ethereum, and there are other techniques like to provide more scalability to either Ethereum or other blockchains. And it basically, for example, like today the problem with scalability is that every single transaction that runs on the network, every single node has to validate that transaction before we accept it as valid. So this means whenever we accept a transaction, at least we know that for sure that transaction is valid. So if you have 1,000 nodes in the network, it means 1,000 nodes would need to validate that transaction before it's accepted. So, but what that means as well is that this the speed of the network is basically kind of like the speed of the weakest node in the network, because until the weakest node validates like the last transaction, you cannot move forward like to the other transactions. So what scalability solutions are trying to do are trying to validate transactions in parallel. So for example, like sharding would divide like the network like into many chains that run in parallel. So instead of like having, let's say, 1,000 validating the same transaction, we'll divide those 1,000 like into 3 to 4 channels, or example. And so instead of like validating one transaction, you validate 2, 3, 4, 5, tens of thousands of transactions all in parallel. So that means like it becomes more scalable. But because we use cryptographic techniques like zero knowledge, we're able to make sure that that transaction is actually valid, even though we didn't have enough time to verify it by every single node in the network. So that what allows it. So it's different, but it's still secure.
Okay. Thank you, Amira. That was a pleasure. What a role model you are. Thank you
So much.
Bye.